Okay, so for effort cue number 6, we have a 4 kilogram block and it is initially sliding on a frictionless surface with a constant speed of 5 meters per second. 2 seconds after the block slides, a horizontal time-dependent force is applied to the mass. The force is then removed 10 seconds later. The graph right here shows how the force varies with time. And so let's see. 2 seconds, okay, 2 seconds is when the force starts, and 8 seconds later, which is 10 seconds, this force stops. Okay, makes sense. Now part A asks us to determine the total magnitude, the magnitude of the total of the impulse, the total impulse of the force acting on the block. Okay, so this is quite easy. To get magnitude, what we're gonna have to do is integrate force with respect to time. So impulse is equal to the integral of force with respect to time. Now we want the total impulse of the force. The force acts from 2 seconds to 10 seconds. So our balance is going to be 2 and 10. Taking an integral of this is the same as taking the area under the curve. So basically the area of this whole thing right here, this shape. This is basically 2 triangles. This big rectangle right here, as you can visualize it, is, let's see, 6 here and up, 6 up. So 6 times 6, that's 36 here. And we have 2 and 3 up, so that's 6 right here. So 6 times 6 plus 3 times 2 is what I essentially did. This is equal to 42 kilograms times mass time divided by accelerator. Divide by seconds. So this is my impulse of the total impulse of the force. Okay. Now part B wants me to determine the speed at t equals 1.5 seconds. Alright. To do this, I'm going to use impulse. Impulse from 0 to 1.5. Oh, actually, I don't need impulse. The problem says that the block is traveling at a constant speed of 5 meters per second for 2 seconds. So that means that before 2 seconds, it's still gonna be 5 seconds. I mean 5 meters per second. So that means my v at t at 1.5 seconds is equal to my v initial, which is 5 meters per second. All right, now part C. Part C says to determine the speed of the block at t equals 6 seconds. Okay, now we're gonna use impulse. So we know that I'm gonna use impulse from 0 to 6. Integrate from 0 to 6 of t dt. This is essentially equal to, so 0 to 6, so here to here. So we're taking this area right here. This is 4 times 6, so that's 4 times 6, and that's equal to 24 kilograms times mass divided by seconds. So that is our impulse from 0 to 6. Now, impulse is equal to the change in momentum, and the change in momentum is defined as mass times the difference in speed. So v at t equals 6 minus v initial. So I'm gonna put these two equations together. So 24 is impulse right here. 24 kg times mass divided by seconds. That's impulse. Impulse is also this right here. M times v at t equals 6 seconds minus vi. Okay. I want to find v at t equals 6 seconds. I know my mass and my vi, so I'm gonna plug them in right now. So 24 is equal to, mass is 4 kilograms. V at t equals 6 minus VI is 5 meters per second. Okay. Now, if we want to solve for V at t equals 6, what we're going to do is we're going to divide this side by 4 first, then add 5. 24 divided by 4 is 6. Then you add 5, that is 11. So my speed at t equals 6 is 11 meters per second. Well, velocity is speed, by the way. Okay. Now for part D, it says to calculate the net work done on the block between t equals 2 and t equals 8 seconds. Okay. Once again, I'm going to use impulse to help me do this. I'm going to find the impulse by integrating from 2 to 8 f of t dt. So I'm basically integrating from here to here. So I have to find the area of this thing right here, this rectangle. As I remember from part A, that's 6 times 6. 6 times 6. And so that means my impulse is 36 kilograms times meters per second. Similar to before, I'm going to set up impulse as a change in momentum equation. So impulse is equal to change in momentum, which is mass times velocity at t equals 8 minus velocity at t equals 2. And now I'm going to put these two equations together. So impulse is equal to 36 kilograms times mass divided by seconds. Impulse is also equal to change in momentum, which is m times v at t equals 8 minus v at t equals 2. Okay, right now I'm going to divide mass to this side. So that means v at t equals 8 minus v at t equals 2. Basically, I'm just flipping equations. So v at t, this is equal to 36 divided by mass. Well, I know my mass. Mass is 4 kilograms. So this is equal to 36 divided by 4 kilograms. And so this reduces down to 9 meters per second. So it looks like the difference between v at t equals 8 and v at t equals 2 is 9 meters per second. Now I can use this to help me find my v at t equals 8. Okay, so first of all, I already know that v at t equals 2 seconds is equal to my v initial, which is 5 meters per second, because no force is acting upon the block until 2 seconds. So that's why it remains the same as vi at v equals t 2 seconds. Okay. Now to solve for v at t equals 8, I'm gonna set up the same thing. V at t equals 8 minus v at t equals 2 is equal to 9 meters per second. Basically what I determined here. Now I'm going to plug in my v at t equals 2 seconds. That's 5 meters per second. So this is v at t equals 8 minus 5 meters per second is equal to 9 meters per second. I'm going to add 5 to this side, so that means my v at t equals 8 is going to be equal to 14 meters per second. So basically I add this 5 to this side. Okay. Now that I have both of my velocities at different times, I can use that to help me find work. Because work is equal to the change in kinetic energy. And the change in kinetic energy is equal to 1/2 times mass times times v at t equals 8 squared minus v at t equals 2 squared. So that is what my work is equal to. I have all of this. I'm going to plug it in right now. So I have 1/2. Mass is 4 kilograms. V at t equals 8. It's 8 by the way, not 5. Oops. Is 14 meters per second. And I square that. Minus v at t equals 2 squared. So that is 5 meters per second. And squared. Plug this all in the calculator. I get 342, and the unit is joules. Okay. Now part E says to calculate the distance traveled between 8 seconds and 10 seconds. Once again, we're going to use impulse to help us solve this problem. So it asks for distance travel from 8 to 10. I'm going to use this as my bound for impulse. So impulse is equal to the integral from 8 to 10 of f of t dt. So basically I'm finding this area right here. That's 2 times 3. So this is equal to 2 times 3. And that means it's equal to 6 kilograms times mass times divided by seconds. So this is my impulse from 8 seconds to 10 seconds. Alright. Once again, I'm going to set up impulse in terms of change in momentum. So impulse is equal to change in momentum, which is mass times the velocity at 10 seconds minus the velocity at 8 seconds. Okay, now I'm going to put the two equations together once again. So 6 kilogram times mass divided by seconds. That's impulse. Impulse is also this right here. So I'm going to set that equal to 6 kilograms times mass divided by seconds. So m basically this right here. And so now I'm going to do the same thing as before. I'm going to divide mass over so I can get the difference of the velocities. V at t equals 10 minus V at t equals 8 is equal to 6 over mass, which is 6 divided by 4 kilograms. And this is equal to 1.5 meters per second. So that is the difference in my velocity. Now that I have this, I can use it to determine both of my my velocity at 10 seconds. I already know my velocity at 8 seconds, so I can use it from the previous problem to help me with this problem as well. So first of all, V at t equals 8 minus V at t equals, this is 10. Minus V at t equals 8 is equal to 1.5. Basically this equation right here, this relationship. Alright, I know that my V at t equals 8 is 14, where is it? It is, where is it? Oh, right here, 14 meters per second. So I'm going to plug this in for V at t equals 8 right here. So V at t equals 10 minus 14 meters per second is equal to 1.5. So I'm going to add this to this side, and that helps me find my V at 10 seconds, which is 15.5 meters per second. Okay, now that I have this, I can use it to find work, which will help me find the distance traveled. Now, I know two relationships or two equations for work. Work is the change in kinetic energy, but I also know that work is equal to force times the distance traveled. Now, the change in kinetic energy is equal to 1/2 times m times v at t equals 10 squared minus v at t equals 8 squared. Now F is, and that's equal to force times distance. I'm gonna plug in all my numbers because I know everything in here except D, which is what I'm trying to solve. So I have 1/2 times mass, which is 4 kilograms, times V at t equals 10 squared, that's 15.5 meters per second squared, minus V at t equals 8 squared, that is 14 meters per second squared, and that is equal to force is 3 newtons, and times distance, which is what we're trying to solve. Okay, this whole side cancels out or simplifies down to 88.5, and this is just, this side is just 3D, not considering units. So 88.5 is equal to 3D. To find D, divide 3 into that side, and D is equal to 29.5 meters. So that is how much the block travels from 8 seconds to 10 seconds. Now part F says to graph the position, velocity, and acceleration for the interval t 8 seconds to 10 seconds. Okay. So here's my position function first. I'll call this x. My axis is x of m, and x-axis is gonna be t or time in seconds. So from 8 to 10. So since there is a constant force applied to the block from 8 to 10 seconds, that means there is a constant acceleration. For a position function for a position function of a block that has constant acceleration, it is going to be a curve. So it's going to look something like this. Make sure it's curved, and it's already traveled a certain distance, so that's why it's not touching 0. Okay. Now for velocity. V meters per second, and from 8 to 10. As I said before, from 8 to 10 there is a constant acceleration because there is a constant force right here. A constant acceleration means that velocity is going to be steadily increasing in a straight line. So the function will look, or the graph will look like this for V versus t, a straight line. Okay. Now for acceleration, meters per second squared, and this is t seconds from 8 to 10. As I said before, acceleration is constant. That means it's going to be a straight horizontal line. It's not increasing like velocity, so it's just gonna be a straight line right here. And that's it.